Okay, so we have discussed about how to resolve the distributed surface forces into the node. And then use that force applied on the node, we can further calculate the solid materials, right? So now those are the surface forces. They are either coming from the traction or applied pressure or the shear stress applied on the surface. But in the reality, there will also be distributed force applied on the body, such as the inertial force, gravity force, electromagnetic force. They all applied on the body, right? So how to calculate, how to resolve those force into the discrete nodes. So here is how we will do it. Okay. So for the distributed force, body force, we can also calculate the potential energies in terms of the degree of freedom times the body force, and then do the body integrations. So here we will have the degree of freedom, body force matrix, and then the dA doing the integration. Because the thickness is constant, so we have the H in front of the integration. Then we will have Q, is for each element, QE transfers, because this is null, so this is a constant, we can take it out. And then the shape function matrix will be with remaining inside the integral. This has the X and the Y. Then times the body force, and then times dA, okay? And then you have the thickness here. So eventually this will result in the degree of freedom times the body force terms. This body force terms contains both the shape function, the volume information, as well as the normalized body force. So this thing actually, this kind of calculation actually tells us if we have the force, this is equivalent to, if we have a body force Bx applied throughout the body, so that can be equivalent to the one big body force, one final force applied to the center of the mass of the element. That equals to the Bx. And then this Bx, the unit of this Bx is Newton per volume. Okay, Newton per volume. There is or sometimes you can the unit can be pound per inch cube. Right. Now this body force we can around the x directions we can actually equally distribute them into the three nodes. Okay, so then it actually equals to AHBX. This is the whole body force divided by 3. And then in all the 3 nodes around the same direction, you can put the same value. Okay. And for the y direction, for example, if we have the gravity force GX, that can also be equally distributed into the 3 nodes around the y direction. Okay. So with that, we can, let me see. Yeah, with that, for the potential energy due to the external force, we can write then in terms of QS. QS is the degree of freedom of all the elements together in the whole solid. So we are now talking about the whole solid. It contains many elements. So the QS transverse times 3 force individually. These 3 forces are applied on all the elements. Okay, in every element you have the concentrated force on the node as Fn, and then traction force or the surface force or the surface pressure Ft, and then body force Fb. Those force later 2 can be resolved into the node as we using the methods we just described. Then all those forces are applied on the node, then times the displacement on the node, you can get the all the potential energy due to the external applied force. For the strain energy term, that's the same. Strain energy term that is equals to 1/2 transverse of degree of freedom matrix times the global stiffness matrix, Ks, times the Q and Qs. Okay, and this global stiffness matrix is actually equals to this Ks actually equals to the element stiffness matrix assembled across the whole solid. And for each element, its element stiffness matrix equals to the volume times the B matrix inverse times the elasticity matrix. C is only the function of elastic property of material, okay? And then times the B matrix, okay? So eventually we will have the expression of whole potential energy of the whole solid. And then when we have those potential energy, we have the total potential energy. When the solid is in equilibrium states, we can take the derivative of the potential energy with respect to the degree of freedom. And if the solid is in the equilibrium state, this term, this differentiation will equal to 0. Once the derivation of this phi term equals to 0, we will have Ks times Qs, these two matrices times together, equals to all the external force. Right? So here you have 2Q is like Q squared, and then 1/2. Take the derivative with respect to the Qs equals to the Q, and then Ks times Q, which equals to this. Here you have only Q times the force. Take a derivative. Q is can be eliminated, and then you only have F term left. So you have Ks Q times F. Okay. And then here, since Q we already know, Q is U1, U1, V1, U2, all the degree of freedom on the nodes. Then given the force, given the Ks matrix, then we can solve all those unknowns, all the unknown Q, unknown F, right? And and we actually have an example to show how we calculated by some simple simple arithmetics. Now this equation actually is called finite element matrix equation for the CST element, for the constant strain triangle element. And then for this case, the assembling and applying boundary conditions are identical to the other elements. For the beam and the truss, for other type of elements, the same approach, same logical method can be used. The stress and the strain calculation in each element can be calculated by the degree of freedom matrix, the node displacement Q. And the strain can be calculated in each element as epsilon matrix equals to B matrix times Q matrix. Sigma matrix equals to elasticity matrix times epsilon matrix. And the epsilon matrix can be further write as B matrix times Q matrix. Okay, and as we discussed earlier, that this stress and strain value in each element, each CST element actually are constant. The reason is because the displacement are linearly distributed, and those linear distributed displacement, which are only the function of x and y, after taking one-time differentiations, they will become constant, and those constants are the stress and the strain. Okay, so that's based on the outline. We have discussed almost every point about the CST element. We start from the displacement and the displacement fitting functions, getting the shape function n1, n2, n3, and then do the interpolations. We can find the displacement on any point within the CST element. Then we can combine that with the theory in the elasticity. We can take the differentiations to get the 3 in-plane strain and get the strain matrix. So the epsilon matrix equals to B matrix times Q, the degree of freedom matrix. Then combined with the material property of the solid, we can determine the stress. For the stress, since all the stress and the force are applying on the node, in the case that the force are not on the node, the boundary condition are the distributed force either on the surface or on the in the body. We also discussed how to assign those distributed force to the node to enhance our matrix calculation. Okay, and then we also talk about the definition of potential energy that has 2 terms. One term is the strain energy. Another term is the potential energy due to the applied load. We have derived both cases how to convert those equation sets into the matrix notation. And also we discussed about the minimum of the potential energy. And by taking the derivative of the potential energy and make that equal to 0, we can get this important finite element matrix equation. Okay, so global stiffness matrix times QS matrix global degree of freedom matrix equals to the summation of external force on the node. Okay, so those are all the aspects of CST elements we discussed. In the next lectures, we will also talk about the different types of elements, such as regular angular elements, but we will follow the same logic. The other elements, we will also start with shape function and then determine the displacement by the interpolation, and then determine the strain, determine stress, talk about how to assign distributed force to the node, and then determine the potential energy and their minimum. Okay, so the logic is the same, but for different types of elements, the detailed shape function, the B matrix, and the form of the results will be all different, and therefore different elements actually will have different applications depending on the specific problems we encounter. Okay. So now let's look at one example together. So here is one example. This example has 2 elements. So element 1 is called E1, this triangle. Okay. Element 2 is E2. So these 2 CST elements, they are sharing one edge together. They have 4 nodes: node 1, N1, node 2, N2, node 3, N3, and node 4, N4. The one edge of the element 2 is clamped here. So the displacement are equal to 0. 2 nodes of element 1, the N2 and N3, they are experiencing the prescribed force. One is around the minus y direction, is a 50K pound, and another is a horizontal force applied on the node 3, 50K pound. Okay, we want to solve the different matrix within these combined elements. What we want to practice is how to calculate those matrices, B matrix, C matrix, and K matrix in each element, and then how to assemble them into global matrix, capital KS. Okay, and then further calculate the stress and strain within the elements. Now, the size and the thickness of the two elements are given. For the thickness, they are the same, h equals to 0.1 inch. And also material behavior, material properties of both elements are equal. They have the Young's modulus equal to 30 mega psi, and the Poisson ratio equals to 0.3. So let's solve them one by one. For element 1, E1, the area equals to this triangle is 1/2 times